Hello, everyone. My name's Travis Steffens, and I'm the Regional Director for the Explorers Club in Ontario, Nunavut. We're having our September meeting today on September 11th, and we're going to have a few we're going to have Dr. Allison, and I'm sorry, I've already forgotten how to pronounce it, but Criscitiello, is that close? That was an if, that was a sort of close, but she'll pronounce it better as we go on. I just want to thank everyone for coming out today. I want to thank Exploring by the Seat of Their Pants, Seat of Your Pants, for hosting this meeting and giving us the opportunity to share our club meetings virtually to members basically around the world, and to those that want to come join us while we share our exploits as Explorers Club members around the world. And I want to thank Kensington Tours, who, although they who normally host our meetings, although we can no longer do that at the time being because of social distancing, I still want to thank them for the immense efforts they've given us throughout the years. And we're all very excited to toast a glass of scotch back in our clubhouse over at their head office in Toronto. So I look forward to that. And so thanks, Jeff Wildner and the team there, for taking good care of us all these years. I'm going to pass you on to our chapter chair for Canada, George Karunas, who has some notes he'd like to share with everybody.
All right, thank you very much, Travis, and hello everyone from coast to coast to coast out there. A few interesting announcements that involve the Canadian chapter. You may have seen in your email today a bulletin from HQ in New York about Fjallraven and our 40% discount with Fjallraven. Now, for a while, we've been partnered with them, but it's been difficult for Canadians to get any kind of discount through them. But our problems are no more. There is a link in that email that allows you to go on and from Canada and get 40% off because of your Explorers Club membership. So that is finally worked. All the bugs have been worked out and we can now get our discount along with the Americans. So that is great news. We also are continuing the Explorers Club 50. That is an initiative that head office or HQ, I guess, is in the process of not quite wrapping up yet. There's still a few more weeks for you to get your nominations in, and it really entails we want to, for lack of a better term, we want to showcase lesser known explorers, perhaps people working in other parts of the world that don't have the notoriety that maybe some of us do have. So we're still accepting nominations for that. It's really easy to nominate someone. It only requires a little 350-word paragraph describing them and what they do. And there's been, at least last I heard, about 120 or 130 nominations already submitted. So it's great. I've submitted 3 already. So I expect each and every one of you to nominate at least one person. That's all I ask. If you know someone who you work with who you think is changing the world and is making a difference, and maybe the world needs to hear about what they're doing, then please do nominate. That would be really great. There's going to be an entire issue of the log that's published with bios of every one of the winners. Is going to be great. Super, super cool initiative. Other things going on. The Discovery Channel grants. That process is moving along quite nicely. For those of you who don't know, I'm actually on the grants committee for that. So I'm one of the people that is involved, along with about almost a dozen others who sift through the applications and then decide whether they meet the mandate of the club and whether they have scientific validity and also the storytelling aspect. And expect, I can't say much right now, but expect a really cool announcement as early as next week. So there's some really interesting stuff that I personally find very exciting. There's some really interesting projects that are coming down the pipe. I wish I could tell you, but trust me, it's coming soon and it's really, really cool. One more thing. The Canadian awards. The Canadian chapter, we have our own set of awards. We have the Stephenson Medal, which is basically a lifetime achievement award, or for special recognition for contributions to exploration. And we're going to be opening the nominations for that very, very soon. There'll be an announcement in the next newsletter. So the Stephenson Medal, and then as well for the Citation of Merit. So every year we offer one Stephenson Medal, but you can have, or we can have, multiple winners of the Citation of Merit. So those nominations will be open very, very soon. And there'll be a couple of announcements about that to remind you to nominate people. There are a few people that were nominated in the previous years whose nominations carry over to this year. I know I think there's two. I can't say who, but there's two nominations. So if you nominated someone last year or the year before and they didn't win last year, then their nomination is still valid. If you have any questions, feel free to contact either me or David Bing. He's the head of the committee for awards and honors. So that's going to be ramping up in the next couple of months. The deadline is at the end of November, I do believe. But in addition to that, the actual Stephenson Medal itself, I'm very proud to say that we have a bunch of them being fabricated right now as we speak, which is great. I managed to, pardon me, managed to get a hold of Jeff Wilner while he was traipsing around Europe with his family, and asked him if he would be willing to sponsor the medal. And he said, not only am I willing to sponsor the medal, let's do 5 of them. So now we're good. We have medals now for the next half decade. So we are in great shape for that. So thank you, Kensington Tours. Thank you, Jeff Wilner, for being such a generous sponsor for our awards. So we're in a great position for that, because that's one of our biggest expenses as a chapter. It is our biggest expense as a chapter. So that is great. So lots of good news, lots of really cool stuff coming up. I've been able to spend a lot of time working with headquarters on a whole bunch of issues that we're going to be able to benefit from. So stay tuned for lots more really cool news. And for now, I think I'm just going to pass it back to Travis. If anyone has any questions right now, just let me know. Otherwise, Travis, back to you.
Thanks, George. Alison, do you mind just pronouncing your name so I don't say it wrong the second time?
Criscitiello.
Thank you very much. All right, it's a real pleasure to introduce Dr. Alison Criscitiello. She is the director of the Canadian Ice Core Laboratory, which I believe she is sitting in right now, which is at the University of Alberta. She's an ice core scientist with extreme field experience in Antarctica, the Canadian High Arctic, Greenland, Alaska, and the Canadian Rockies. That's a lot of ice. She has a BA in Earth and Environmental Science from Wesleyan University. She has an MA in Geology and Geophysics from Columbia University, and a PhD in glaciology from MIT slash the WHOI, which I looked up, but I don't remember what that stands for at the time. Mountain, bunch of wonderful letters. What was it?
It's the Woods Hole Oceanographic Institute has it's a joint degree from there in MIT.
Wonderful. So she's got the credibility to talk about ice cores, probably more so than anyone else in the world. What I find fascinating, she's also the co-founder of Girls on Ice Canada, which Girls on Ice is a tuition-free science immersion suburb wilderness expedition that will be going on hopefully in 2021. And that's very exciting. She's a National Geographic explorer, a fellow of the Explorers Club, as an ice core scientist, as I mentioned before, a high altitude mountaineer and alpinist. Basically, she's done a lot of stuff. She's got multiple publications. She's a world expert on ice. So it's very exciting to share with you someone who knows more about ice than more people, except for maybe those that drink a lot of bourbon. Wonderful to have you here. Thanks so much. I'll pass it on to you.
Okay, thank you. That was a lovely intro. I'm going to share my screen with you in just 1 second. Okay, you see that okay? Okay, awesome. Well, thank you so much for having me. I was really pleased to be asked. It's an honor to talk to you. Everyone in this club is amazing and it's such different backgrounds. And because of that, I'm really hoping that everyone can take something different away from today. And just this little talk that gives a taste of some ice coring projects that I'm leading right now that I thought might be of interest to this group. So I'll mostly skip this since that was a really nice intro, but I sort of have a dual life. I'm an ice core scientist, and I alpine climb and mountaineer sort of professionally. And the reason that I think this really helps me is I core in some very, very difficult to get to places. I can core at altitude, and this makes me really one of the only women who can do this in the world, having the dual altitude mountaineering and ice core science background. So this is what I wanted to talk to you about today. I'll give a quick how and why of ice coring, and then I'll present some exciting new results from a couple projects that I'd really like to highlight. One investigating some subglacial lakes on Devon Ice Cap in Nunavut, and one project looking at environmental contaminants in the Canadian high Arctic. And lastly, I'll just highlight a couple ongoing and future projects that I thought might interest this audience. So first of all, I'm sure this is an overview for some, but I just like to go over why we go through the trouble and expense of drilling ice cores in these really hard to get to places. Well, they allow us to investigate past climate and environmental conditions prior to the 1970s, prior to when the satellite era began, which make them one of our most powerful tools for studying the Earth and climate on long time scales, and how humans have impacted both. Now, ice cores, the chemistry of ice cores in particular, offers a almost endless number of tools to investigate past climate. And I list here just a small selection of things that we commonly utilize ice cores for. There are many elements that offer useful isotope ratios for reconstructing different kinds of histories. So for example, we can use plutonium-239 as evidence of previous nuclear weapons testing. And we commonly use oxygen isotope ratios to reconstruct temperature in the past. Now, there's major ions I listed here second. We commonly use these things like sodium and chloride, sea salts, which actually can tell us a lot about sea surface conditions in the past. And then there are other major ions that offer different insights into paleoclimate. For example, ammonium, which gives us a history of forest fire activity in the past. And then I list here my personal favorite and specialty, this MSA, it's methanosulfonic acid. And this is actually something that comes from phytoplankton in the ocean. And it's something that gets recorded on ice sheets and basically is a record of sea ice in the past. So this is my particular area of expertise, is developing the use of that particular ion as a sea ice proxy in ice cores. Now, the last category here is something I've only worked on the last couple of years, but is becoming a hotter and hotter topic, using ice cores really to study more recent changes in our climate and environment. So I'll talk about some organic contaminant records in Arctic ice cores that have helped us to understand how even these remote polar regions can be impacted by chemicals that humans have introduced into our environment. So I also thought I would just show a quick how of the two drills. They're sitting in a room behind me, actually. So there's two different drills. The sort of class of ice core drills is based on their maximum depth that they can go to. This particular one is called the Canadian Eclipse drill. And it's shown here on the left. So this was actually on the Kaskawulsh Glacier two seasons ago in Yukon. It's shown in its horizontal position, but it's a tipping tower drill. So that's sort of the ice retrieving position, and then it just pivots and swings up to a drilling position. And on the right, you can see what the inner barrel of this drill looks like. It has sharp cutters and spacers that let you change how aggressive the cutting is. And then people often ask, how does the ice actually stay in the barrel? There's little windows that are marked as as core dogs, and they're little, just one-way spring-loaded, like slivers of metal that engage the ice and hold it precariously in the barrel for its travel back up the borehole. So I'm going to show a quick, it's a sped up video from 2 seasons ago in Antarctica using this drill. So this is the ice retrieving position here. So it's drilled down, and then I'm running it in reverse, which we do especially when you're drilling at depth and you had to put fluid down the hole to maintain a certain pressure. So you can see this slush coming out, which is actually basically snow dust mixed with the drilling fluid. It's a kind of coconut oil. So yeah, you run as much of this slush out as you can. And then these tipping tower drills have an inner and an outer barrel. So we have to remove the inner barrel every single meter that we retrieve. So we disconnect the inner barrel from the rest of the drill and then bring it over to a core processing area that we always set up along the side. And that's just a plug of those ice chips as well. And then there comes your, hooray, a meter of ice. So that gets repeated every single meter for hundreds and hundreds of meters. So as you can imagine, when you're at the surface, there's very little travel time of the drill. You can drill tens of meters in a day. For that particular clip was from almost 300 meters deep. When you get that deep, you only get a couple meters a day. The travel time of the drill is so long. So the other system that we commonly use, I also have one of them, and I really should have grabbed it because they're right behind me, but this is what it looks like. It's called a Kovacs, and this is much more portable. They drill usually 20 to 30 meters, absolute maximum. It basically is just that exposed inner barrel, and you manually add extension rods to it. You can, in the middle picture, I'm using a motor to drill down, but the really cool thing about this drill is you can use it completely manually. So you can drill down and pull the whole thing up totally manually, having no fuel anywhere near the hole, which is really, really important for some of these more recent contaminant studies where we just can't have any contaminants at all near the hole. So I'll show you another quick sped up video just of this one. So this was, when was that? A couple of seasons ago on northern Ellesmere Island. And it's really the same principle. It's just that you're manually doing all of it and you're manually extracting. So we add an extra meter extension rod at a time and then remove them. And then you just extract that meter of ice you've just drilled from the inner barrel, bring it to a, more open air processing line. Usually this is what it looks like in the Arctic with these systems. And then back down the hole you go, adding the extension rods as you go down and start all over again. How do I go? Yeah, so that's a really brief how and why. So did I skip them? No. Yeah. So now that we had a quick overview, I'd like to look at some really interesting new results from some new projects in the Canadian Arctic. I'll show you the most recent findings on Devon Ice Cap subglacial lakes, and then we will have a look at the fate and transport of contaminants to the Canadian Arctic, with an eye towards how things that we use in our daily lives can reach and impact even the most remote parts of our planet. So some of you may have seen this impressive discovery, because it was 2 years ago now, by a colleague of mine here at University of Alberta, Anya Rudishauser, of a subglacial lake complex beneath the Devon Ice Cap in the Canadian High Arctic. And this water body presents a really unique scientific opportunity because it's an extreme potential microbial habitat with what we believe to be some of the coldest, saltiest, darkest, and most pressurized conditions on Earth, similar to microbial habitats that are hypothesized to exist on Mars, and one of Jupiter's and Saturn's icy moons. But due to the limited coverage of the surveys from that initial study, the full extent and the characteristics of these lakes have remained pretty unknown beyond just that they exist. So since that came out, myself and Anya Rutishauser and Ashley Dubnik, who is also a scientist here at U of A, have done some targeted aerogeophysical surveys over the Devon Ice Cap, which have provided supporting evidence for one of these two subglacial lakes. And this is in review right now. It will be out soon. So there's newly resolved shorelines of these lakes that show that they're over 25 square kilometers big, which is more than twice the size that was reported in the initial discovery, with water depths of up to 140 meters, which is pretty unbelievable. And furthermore, we find evidence for this extensive brine network because it's underlain by a salty bedrock, which is partly why it can remain liquid water under hundreds of meters of ice. It's pressurized. It's also super, super salty. And our ultimate goal with this project, this is the sort of 5 to 10 year goal from now, is to build a biologically clean subglacial access hot water drill and sample the lake. Okay, moving on. I also really wanted to highlight some recent work on the environmental contaminants that I mentioned. And this is actually thanks to a really strong collaboration with Environment and Climate Change Canada, who have some unbelievable scientists and capabilities in terms of what they can measure. So I hope I don't get too jabbery here, but perfluoroalkyl substances, or PFAS, these are a large class of chemicals that are largely used in two commercial applications, fire suppressant and non-stick technologies, but these are a class of chemicals that include things that go into like some flame retardants, Gore-Tex. It's stuff that we use commonly. And some of this class of chemicals are persistent in the environment. So they've been dubbed forever chemicals because they don't degrade in the environment. So I drilled a suite of ice cores, first on Devon Ice Cap, to allow us to investigate the potential transport of these chemicals to the remote Arctic. And in short, the results showed that some of these PFAS have continuous and increasing deposition on the Devon Ice Cap, despite North American and international regulations and phase outs. So we, through modeling and some other components of this work, we showed that it's the result of ongoing manufacturer use and emissions of these compounds in regions outside of North America. And we also showed that there are strong Eurasian sources, particularly from continental Asia. And so those are the largest contributors actually to the global pollutants impacting Devon Ice Cap. And really this assessment has allowed us to characterize the depositional profile of some of this class of chemicals on the Devon Ice Cap, and really to further our understanding of the long-range transport mechanisms of these persistent pollutants. It's so unbelievable to be in these places that seem, yeah, they just still make me tear up. They're so remote and pristine. And then you come back with ice and analyze them and find all these contaminants. So this is just another one that it got a lot of attention recently, and I thought it might be interesting. So in another study, we utilized some tandem cores I drilled on Devon Ice Cap, but also on Mount Oxford, which is very northernmost Ellesmere Island, to investigate the deposition of short chain PFCAs. So what are these? When CFCs were discovered to be ozone depleting and also greenhouse gases, they were regulated and phased out in the Montreal Protocol in the late 1980s. And CFC replacements included compounds that have lower ozone depleting potentials. That was the whole, well, one of the main points of the Montreal Protocol. However, the CFC replacements that then started being produced and put into our environment undergo atmospheric transformation to produce these short chain PFCAs. And some of these are persistent organic pollutants themselves with no known degradation pathways. So they also now have been shown to make their way into the most remote environments on Earth. And we care about this mostly because we don't actually know a lot about these short chain PFCAs, but a few preliminary studies have actually shown that they are highly toxic to plants and some invertebrates. But again, I think to me, the more concerning thing is actually just that there's so much we don't know about them, and they are being globally distributed already. So these new cores, love that photo. These new cores from Devon and Oxford, northern Ellesmere, have shown a 10-fold increase in these short chain PFCAs between 1986, the Montreal Protocol, and 2014, when I drilled that particular core. So this was the first multi-decadal record of this class of chemicals in the Arctic. And our results suggest that the CFC replacement compounds mandated by the Montreal Protocol are the dominant source of some of these short chain PFCAs. And this paper came out very recently, and it got a lot of attention for a number of reasons, I think you can imagine, but overall, I think the Montreal Protocol is to be celebrated, which I have made a point of saying every time I'm asked. It is hugely to be celebrated. I think these results also show the need for a more holistic approach when we're deciding to ban and replace chemical compounds, because chemicals degrade, and developing a strong understanding of how they degrade in the environment and what they will ultimately degrade to is vital. So those are some new projects that I'm really proud to be a part of, and have been pretty important. And then I just thought lastly that I would highlight two current projects. They've started already and are ongoing in the next couple of years. Neither of them are polar, but both are in critical and iconic mountain regions of Canada. One is the Columbia Ice Field in the Canadian Rockies, and the other is Mount Logan in Yukon's Kluane National Park. I will just give a little background on the Columbia Ice Field project, because it's cool, and I got to just speak to Joe in the field live when I was up there in April drilling the first cores for this project. But this actually focuses broadly on trying to understand and quantify historical deposition rates of various organic and inorganic pollutants, and in doing so, we really hope to get a handle on what is melting out and making its way into the rivers that drain off of the Columbia Ice Field, because this impacts water quality through the release of contaminants. And the really interesting thing about the Columbia Ice Field is that just because of where it sits and its altitude and just where it's located, legacy contaminants that are no longer in production but used to be, actually end up on the Columbia Ice Field. I'll talk about that in 1 second. So just a very short bit of background on this. The water, of course, is a very critical natural resource in Western Canada, and the Saskatchewan, Athabasca, and Columbia rivers, which eventually drain into the Atlantic, Arctic, and Pacific Oceans, all originate in the Canadian Rocky Mountains. So these river systems are important sources of drinking water for many major Western cities, such as where I'm sitting, Edmonton. That is the source of Edmonton's drinking water. And melting glaciers and ice fields have been shown to be sources of metals, of organochlorine pesticides, OCPs, which are no longer made, though that's a legacy contaminant. It was a pesticide, and other pollutants to downstream freshwaters. So contaminants that accumulated over many, many years can be released very rapidly into downstream ecosystems in a warming world. So these legacy contaminants that we're concerned about include things like DDT and PCBs and brominated flame retardants. Again, things that aren't in use or in manufacture anymore. So they were historically used, of course, at lower altitudes, but they cold condense on the Columbia ice field because of its location, like I mentioned. So by cold condense, I mean that they enter the gas phase at low elevations where air temperatures are relatively warm, and then they condense out of the atmosphere when they're transported into higher, colder regions. And these are just some photos from April, from the first shallow coring season I completed with a really small team. And we will return for sure next spring. And assisting me was my PhD student. This was her first time in the field, and it was in the -30s, which is not what I was shooting for. -10 is a really nice temperature to drill at. -20s are okay. You don't actually want it any more warmer than -10 because sun on the drill parts can cause some melt and some issues. But anyway, -30s is cold if you haven't dealt with it, but she did amazingly well. And so these are the cores that we just got in the field. And here are some of the things we plan to analyze them for, most of which I've already discussed. Things such as major ions, which give us these various climate histories. Oxygen isotopes will give us temperature record. Black carbon, which can tell us about the forest fire history. And then we have enough sample as well to measure numerous environmental contaminants that I talked about. We will measure the PFAS and some of these, actually, hopefully we'll measure the short chain PFCAs as well. And one other thing that I didn't mention that's particularly interesting here, where a lot of folks care about wildfire history, is black carbon. And ice cores offer a really good record of black carbon in the past, which together with some other things we can measure, these PACs, they allow us to assess how that carbon from forest fires that's landing on the ice surface is actually increasing melt. So this spring, we also took discrete snow samples for these legacy pesticides, and also for microplastics, which is what you're looking at here, the Tyvek suits and everything silicone and Tyvek, because we're measuring for tiny bits of microplastics that have been transported up there, and also can, of course, potentially be released into downstream environments and drinking water. Okay, last up, my very favorite, I just wanted to highlight this one last scientific expedition to Canada's highest peak. I will be leading 2 seasons on Logan's Summit Plateau to drill a surface to bedrock ice core with colleagues from University of Maine, who are the other folks in the world with this funny background that I have. So this was originally planned for 2020 and 2021. Of course, pushed everything back a year due to the pandemic. So in May of next year, I'll lead a small team up the King's Trench mountaineering route to the Summit Plateau, and we will use ground penetrating radar, or GPR, to look at the internal structure of the ice and to help us locate the ideal drilling location where we have the best shot at drilling into the oldest ice that's up on the plateau. And then in May 2022, we will return again to the Summit Plateau, and we will drill a surface to bedrock core. It'll be a couple 100 meters deep. I won't know till we do the radar. And this new Mount Logan ice core record will help us to better understand the regional responses of our coupled climate system to phenomena such as El Nino during past climates. And we are yeah, our best estimate right now is that the record we will retrieve will be about 30,000 years old. Yeah.
What altitude will that be? Will that work be done at?
It's at 5,500 meters. Yeah. This project is really interesting. Yeah, in part simply because of the difficulty in drilling at 5,500 meters. It requires not only a background in ice core science, but in high altitude mountaineering. And so this scientific expedition has interesting support and financial backing from these three entities listed here that are, yeah, I've never had a science project funded by alpine clubs or a geographical society, but yeah, it's unique. And I was on Logan a couple of years ago, and I skied from the summit to the base, and I told myself I would never go back. It's one of the coldest places I've ever worked, including the middle of East and West Antarctica. But I'm going back twice now. Yeah. Anyhow, you can follow any of this work if it interests you. Yeah, I hope something was interesting to everyone here, and please feel free to get in touch if you want to discuss any of the science. Thank you.
Wonderful. Thank you so much, Alison. That was incredible. That would I think I could ask you a million questions. So next time I go to Edmonton, I'm just going to look you up and I'll go ask you to go out for a beer, because I think there's an amazing work that you're doing. And I love that you're able to combine some of your passions together into research, which is fantastic. If I'm going to post it, I think you have a few minutes before you have to go. So I'm going to ask a question. I'm going to see if anyone here wants to ask a question as well. Like I said, I could ask you a million questions, but I'm really fascinated about I've lost track of but the CFCs that we got rid of in the Montreal Accord, or whatever it's called. I distinctly remember when that happened, and I remember it being a big landmark for the environment, because we were really concerned about ozone layers. And then recently, I didn't realize that this research was coming out of your lab. I had read about the issue of these replacements being stuck in the ice in remote areas, which is a long-term problem. So I guess my question is a bit twofold. One, do you think we have the stomach as a society to make those landmark environmental decisions like we had done in the 70s and 80s again to solve this problem? And the second is, what is you addressed this a little bit, what is this as dire of an issue as CFCs were originally? Is this something we should be focusing on removing now?
Those are the best questions. There are things I'm wondering too, but I mean, it's hard to compare a hole in the ozone layer to these increasing unknown chemicals that have been shown to be toxic to some plants and invertebrates. They're two different problems. But I think what we do know is Cora Young, who was a co-author on this, was quoted as saying, all we've done is kick the can down the road, which just always sticks in my head. It's a new problem. It, in some ways, if you had to compare, maybe isn't as bad as a hole in the ozone layer. But it may be widely toxic and we don't know. But the rate at which it's increasing and the places that we're finding it increasing just mean that we have gone on another grand experiment that you can't turn back. So I guess all I can really say is I would hope that more not out in the world experiments happen in terms of degradation pathways of chemicals before they are released into the environment and allowed to be produced at mass scales.
Yeah, it's this is the kind of things that, from an environmental perspective, I do. I study lemurs and extinction in lemurs, and there's acute problems that happen that are very clear, and the ozone layer is an acute problem that we can see. but the chronic issues that have long-term consequences where they don't appear easily fixable are the stuff that actually scares me. And so this seems like a thing we should be more worried about than we probably are.
Yeah, I think you're right. These sort of diffuse problems don't get, they don't get the attention in a way. I think what will get the attention would be the unfortunate, which is that if more biological scientists do determine that there's a toxicity to people or to certain animals that people care about. I think that might kickstart, another phase out.
Amazing. Yeah, the work you do is incredible. Does anyone else who's on camera here have any questions for Alison while she's here? George does. Go ahead, George.
Yeah, a bit of a procedural question for you, a two-part procedural question, actually. Yes. Have you found or have you experienced any difficulties with glacial surface melting corrupting your ice core samples, layers mixing and such? And have you ever had a catastrophic equipment failure when you've been out in the middle of nowhere? Because this system seems like it's got a lot of parts that have to fit together just right. And if you're in the middle of East Antarctica, there's no help nearby.
Oh, yes, there's always disaster. The melt question, yes. And in fact, the fact that certain places are starting to see surface melt is one of the drivers of how the ice core community prioritizes where we drill right now. It's why I'm on the Columbia ice field right now. And places like Devon Ice Cap, which is not super high Arctic, it's not like northern Ellesmere, there is very significant summer surface melt. Like we can't even go, you can't go there in July. You can't land where we drill because the surface is too wet. So what that does, of course, is completely destroy the upper part of your paleoclimate record. Mm-hmm. So in the Rockies as well, up on the Columbia ice field, or the places in the high Arctic that see summer melt, we drill it, we still measure everything, but you can see all the isotopes, all the major ions are all washed out. You lose your annual signal. And then as soon as you get through the years where there's summer melt, then your beautiful annual signals all pick back up. So it doesn't render them useless, but if enough years go by and enough surface melt can percolate way down into the snowpack, yes, you can completely lose these records. Yeah. So melt is no good in general. Your second, catastrophic failure. Okay, I'm
sure you've got a story or two.
Well, yeah, nothing really catastrophic has happened in Antarctica, which is good. It's just so much harder to get something if you need it. But there have been quite a few lost Kovacs systems, only down 20 meters or so, not by myself, but this is just kind of, they're notorious for getting stuck. And if they do get stuck, all you can do really is, I usually take like a 5-gallon thing of ethanol in the field, and all you can do to get your drill out is dump it down the hole and wait a little bit of time and hope that it melts out. And if that doesn't work, you literally can't retrieve your drill. That hasn't happened to me, but to a lot of people around me. The only thing I ever drilled into that I didn't know was there was in the high Arctic on Agassiz ice cap. In the 70s, some glaciologists went up there to drill and left behind basically what appeared to be their whole camp, tents and stuff. I drilled into like a cavern and then excavated it, and I drilled straight into their old camp, which is very unlikely. What
are the odds?
Yeah. No damage was done. It was just interesting.
Thank you.
Yeah.
Carol has a question for you.
Hi, Alison. That was amazing. I found it so inspiring, and congratulations on your work. And I love how you also are like, this was collaborative. And so my question is, well, I collected garbage on Svalbard and brought it home, and it's in a museum in Ottawa. So I'm so interested in, okay, the deeper story of that plastic. What's your message to young explorers, especially young women or girl explorers? Because I know you're a big advocate and involved with Girls on Ice.
Yeah, oh, I'm so glad you asked, and thank you. Yeah, there's a lot of, I feel like there's a lot of research that has come out in the last couple of years that has put statistics to what we've always known, which is that having women and minorities at leading science, leading big science, means better science. And the most important thing to me, which is why I founded Girls on Ice Canada, is that girls see themselves doing this. Like if they look to see who is doing what they might want to do, they see someone who might look like them. and that has been one of the most important things to me. And it doesn't actually have to do with the science of it. And something too, I think I would say to young people is, it's not a hopeless field. Sometimes people are like, oh, that must be so depressing. You're going to these places that are changing so rapidly, and you see this change. And I think it's quite the opposite. And when I started doing what I do 15 years ago, there was no young grassroots voice behind this climate movement, and there is now, and it's strong. And this has changed I'm in my 30s. This has changed in my lifetime. It's unbelievable. And that the power is in them.
All right, Alison, I'm going to jump in for a second. I want to share my screen here just for 1 second. I want to share an image if it'll let me. Oh, what's Google Chrome doing today? Okay. I've got to, there we go. All right. Okay, it's not going to let me, but I'll share with the group afterwards. There's this great picture when you did the live event for us from the Columbia ice field. You've got a hole dug in the ground. You have a whole system built behind you of boxes to block the wind. And you did just an incredible event for us, a National Geographic Explorer classroom from there. So my first question is, now that it's passed and you look back at it, I've got to know how cold was it standing in that pit and talking to us for like 45 minutes plus?
Oh, actually, it was not. That was the nicest moment. You could see it was really sunny. Thank goodness. The wind was howling, but I think it was around -20. But I set up a wind shelter, so no wind chill.
Yeah. So then I'm curious about, when you select a site to drill, is there anything, any kind of preparation in advance, or is it kind of just look around, point, this looks good enough, let's go?
Yeah. Yeah, that's exactly why I have to go to Logan twice. So historically, before these fancy radar systems, yeah, glaciologists used to just land and drill. But it's hard to pick the best spot that way, just from looking basically at the surface topography. But now we always drag a radar system around in a grid on domes or plateaus, which will somewhere contain the best place to drill. And we look at the internal structure of the ice from under your skis all the way to the bedrock. And we find the place that looks to have the most continuous record with no alterations to the stratigraphy. We don't want to see sheared layers or deformation, same as you would think in a sediment core. And we try to find places where there's no horizontal velocity. There's basically no movement of the ice in the horizontal direction. So it's just this perfectly preserved record. And this is why the GPR, these radar systems have come such a long way. That's why we think we can probably get 30,000-year-old ice on Logan, the oldest ice that is sort of modeled to be sitting up there.
Yeah. So it looks like screen share is cooperating. So I've got the image up here. This is one of my favorite pics of the field. Just, you can see how remote it is. You
Just
can
chatting on an iPhone.
And just with the iPhone, it's awesome. So thank you for everything you've done for us the last couple of years and doing events live out on the glaciers.
Oh my gosh, thank you. It's so cool to do that with you. Yeah.
Awesome. Joe, is there anyone with any questions on YouTube if you want to take a quick peek? And then if anyone else here while we're waiting for that has a question, I know Alison has to go pretty quick, so we don't want to take up too much of her time.
Yeah, there's definitely people tuning in, so don't be shy. Those who are tuning in via YouTube, use that chat sidebar on the right and send us in a question. We've got about 8 minutes left with Alison.
And while we're waiting, Alison, if you besides Logan with this fantastic 30,000 year record, is there another place in the world where this would be ideal to do a similar project? Is there anywhere else besides that?
Oh, like non-polar records that are being prioritized?
Yeah.
Yeah, there's a number. Places that have ice that are sort of more unlikely, like Peru. Some of the glaciers in Peru are being prioritized by the European Ice Coring Group because of increasing melt and these records getting destroyed. Where else? Yeah, sort of the main Andes, places you can think of outside of the poles that contain ice, but have a lot of positive degree days in the summer.
Is it the horizontal movement must be really tough because a lot of ice and ice fields are actually moving in a particular direction. So getting a place that's relatively stationary must be a needle in a haystack sort of situation.
Well, yeah, that's right. I mean, that's why you can't really just drill on a glacier. So on the Columbia ice field, for example, the only good climate record exists up on Snow Dome. It's not one of the, it's not the Saskatchewan Glacier. It's not one of the moving glaciers or the Athabasca. It's the dome that's just sitting there. And if you were to look at the flow lines, it's accumulating and they're moving toward the edges. But a glacier that's actually moving will not give you a good ice core record. Yeah, so when we sort of sort out where to go with these radar systems, we're looking at topography and also bedrock topography if we have that data for these kind of dome regions, the summit of plateaus and domes. Yeah.
How did you get interested in this line of work?
I'm from Boston. So it seems unlikely. I guess through my love of mountaineering and alpine climbing, actually. It was really through the recreational side because I was a climbing ranger in the U.S. National Park Service for years, and then I just loved living and working on ice. Yeah, and I decided to go back to school to study it when I went to get my master's. So I would say it was really through my own enjoyment of the landscape.
Alison, I do have a question that came in via YouTube. This is from Dwayne Derrick, and they're wondering about stacking of ice. So, maybe somewhere like the Columbian ice field, how many inches per year are added, or is it being added right now?
Oh, good question. So that's the accumulation rate, how much it snows per year, which varies hugely depending on where you're talking about. In West Antarctica, one of the highest accumulation areas of the Antarctic, it snows many meters, like 3+ meters per year. So if you drilled one of these sort of Kovacs shallow 20-meter records, you're only going to get a few years. But in places like the Columbia ice field, a lot of the Canadian high Arctic, depending on where you are, the accumulation rate, say it's a meter or a half meter, something like that. And then it gets compacted, of course, as it moves down and down in the snowpack. So as a very average number for both of those general regions, if you drilled a 20-meter core, you would get, before the satellite era, you'd get back probably to the 1950s, something like that. But yeah, it depends on how much it snows every year. Good question.
No, we've got another question online too we can squeeze in. This one is about, I think you kind of answered this a little bit, about an interesting place for an expedition, but if you could pull one together now, pre-COVID times, and go anywhere, where would it be?
Ooh. Well, I've never been to the Western Canadian high Arctic. And this is actually a hope. I hope this will happen within a few years' time. But Axel Heiberg Island is, it's logistically much more difficult to get to. It's nowhere near Resolute, which is kind of the hub for logistics for high Arctic work. So yeah, it's just a lot more complicated logistically to get there. But there is an ice cap on Axel Heiberg that I would love to drill. I hope that I do in the next few years. It hugs the Arctic Ocean instead of Baffin Bay. So most likely the record there will tell us something very new, something more about changes over time in the Arctic Ocean.
Awesome. Well, that brings us to nearly 8:30. So I wanted to thank you very much for taking the time to share with you your research. You're obviously very passionate about it, and from the questions that I've seen people ask and the interest on people's faces, this has been a great talk that I'm very excited to continue to share with the club, because we'll have this recorded for other members who couldn't make it today. Thank you very much, and I appreciate you taking the time. I know you're very busy. And I appreciate you coming out.
Thank you all so much. It's really a pleasure to talk to you all. Thank you.
Thank you.
Great.
Awesome.
Thank you so much.
Alison.
Okay, bye-bye.
See ya.
Bye-bye. Wonderful. This has been another a meeting of the Explorers Club for Ontario and Nunavut, brought to you by Exploring by the Seat of Your Pants. Thanks, Joe, for all your help, and thank you everyone for coming in.